Hi, welcome back. In our last lecture on networks, remember we've talked about the structure of networks, things like their degree, their path length, their clustering coefficient, and then we talked about the logic, how networks form. In this lecture, we're going to talk about the functionality of that structure. So when a network has some structure to it, it has some degree distribution, it has a connectedness, it has a clustering coefficient, and what we can ask is, how do those properties of that network allow it to carry out different functions? Now remember, when we think about those functions, they're typically emergent. When people form a network, they're not thinking about the entire network. They're just thinking about their own connections. So those properties, the network structure itself, just emerges from the logical process through which it forms. And we want to talk about how that structure has functionality, so it can do particular things. We're going to start out by talking about something known as the 6 degrees phenomenon. And let me explain where this comes from. It comes from 2 famous experiments in social science. So Stanley Milgram, in the 60s, asked 296 people from Nebraska to get a letter to a stockbroker in Boston. Now the rule is they could only send the letter to someone they knew on a first-name basis. And what he found is that on average of the letters that got there, it took about 6 steps. Now Duncan Watts, almost 40 years later, redid this experiment with 48,000 people on the internet, and they had to send an email to someone they knew on a first-name basis and try and get it eventually to these, target people all around the globe. And what he found again, that the average number of steps was 6. So it took typically 6 steps to get from one person to another. So there's a 6 degrees phenomenon that we want to understand how that can be. So we're going to do this by looking at a variant of the small worlds network. So we know that social networks have this small world sort of structure to them. We're going to use that to explain how you can get 6 degrees of separation. So when people form friendship networks, they don't do it with the intent of creating a 6 degrees of separation world network. We're going to show how that just emerges from the structure. So we're going to start out by simplifying the small world network as follows. We're going to assume that each person has a group of friends. C of them belong to a clique. So your clique friends are all going to be friends with each other. And then you've got a few random friends off to the side. So you've got C clique friends and R random friends. Let me show you what this looks like. So here's a clique. And everybody within the clique we're going to assume is friends with everybody else. So it's got a very high clustering coefficient. And then each person in the clique also has one random friend, and that random friend belongs to some other clique. Now I need to introduce a new idea. This is called a K-neighbor. So a 1 neighbor is someone that you're connected to. So that'd be a 1 neighbor. A 2 neighbor is someone who's connected to someone you're connected to. And a 3 neighbor is someone who's connected to someone who's connected to someone who's connected to you. So what you get is you're 3 steps away. Now if there's also a connection between these 2 people, so this person is both 1 step away and 3 steps away, we would classify them as a 1 neighbor. So that the shortest distance between one person and another. So your 3 neighbors are the people who are 3 steps away, but they're not 2 steps away or 1 step away. So 6 degrees of separation is going to mean that someone is 6 steps away, but not 5, 4, 3, 2, or 1. So let me show this graphically. I'm looking at this person here. The 1 neighbors are going to be the 2 people that he's directly connected to. The 2 neighbors aren't going to include these 2 people he's directly connected to, but it will include these 2 people who are connected to the people he's connected to. So 1 neighbors are who you're connected to, 2 neighbors are the people who are connected to the people you're connected to. That's the idea. Now we're going to use this to show how you can get 6 degrees of separation. Here's how it works. If you look at a person in this random clique network, what they've got is who are their 1 neighbors? It's their clique friends, which will represent by this C, and then their random friends, which will represent as being red. Those are the 1 neighbors. Now who are the 2 neighbors? Well, their 2 neighbors are their clique friends, random friends, that's these people, their random friends, which are these 2 people, and then finally their random friends, clique friends, which are these people. So all I've done is they've got clique friends and random friends. I've just sort of written all this stuff out. But what about CC? What about the clique friends? Well, my clique friends are just equal to my clique friends. So if I think about how I get my 2 neighbors, I just take clique random, clique, but I don't add in clique because those are just the clique friends. All right? What about the 3 neighbors? Well, I do the same thing. I've got my random friends, my random friends, clique friends, right? My random friends, clique friends, random friends. So who are my random friends, clique friends, random friends? So I'm going to click. I've got some random friends. My random friends belong to a clique. And then I've got their clique friends, random friends. That's who these people are. So I can just write down all possible combinations of 3. Random clique, clique random, random clique, that sort of thing. However, I can't write down random click click. Because if I have 2 clicks in a row, my random friends, if this is me and I've got a random friend and he's in a click, my random friends click friends, which are these people, well, their click friends are the same people. So random click click is the same as random click. And click click random is the same as click random. And click 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 is just my same click. So all I have to do is write out all these combinations, and that gives me the total number of 3 neighbors. Well, let's do this in a real case. So let's take, I've got 140 click friends and 10 random friends. And this is actually approximately the number of friends that people might have. People have about 150 friends. Most are sort of close to you. So let's compute the number of 1 neighbors. Well, that's just equal to 150. What about the number of 2 neighbors? Well, I've got my click friends, my random friends, click friends, and my random friends, random friends. So that's going to be, I've got 140 click friends, and each has 10 random friends, so that's going to be 1,400. I've got 10 random friends, each one has 140 click friends, so that's another 1,400. And then I've got 10 random friends, each of whom has 10 random friends. So that gives me another 100, which gives me 2,900 if I add all that up. So I've got 151 neighbors. I've got 2,900 2 neighbors. What about 3 neighbors? Well, here I've got random, 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 click, random, click, random, and click, random, random, and then click, random, click. Those are all the possibilities. So if I do this, I'm going to get 10 times 10 times 10, which is 1,000. I'm going to get 10 times 10 times 140, which is going to be 14,000. That's a lot. I'm going to get another random click random, so that's another 14,000. And I've got this, which is another 14,000. And then here I've got 140 times 10, which is 1,400 times 140, which is going to give me 1,400, and then I'm going to get plus 56, which gives me 196,000. So when I add all this together, I'm going to get 229,000 3 neighbors. So that's a lot. I've got 229,000 3 neighbors, 151 neighbors, 2,900 2 neighbors, 229,000 3 neighbors. That's interesting. It's interesting because it helps us understand a phenomenon that's been long known empirically. So in 1973, Mark Granovetter wrote a paper called The Strength of Weak Ties. And what he found in this paper is if you think of the important things that happen in your life, like the job you get, who you marry, where you live, all sorts of important things, it doesn't depend on your 1 neighbors, your close friends. It tends to come from your 2 neighbors and your 3 neighbors. These weak ties, these people who you're remotely connected to, end up having a big effect on your life. Well, let's think about who these 3 neighbors are. So a 3 neighbor could be your roommate's brother's friend, right? 1, 2, 3. Could be your mother's coworker's daughter, 1, 2, 3. Or it could be your high school roommate's, college roommate's dad. Again, 1, 2, 3. So 3 neighbors aren't that far away, and they actually can seem close. They actually become the points of sort of interesting story. Like, I actually got a job with my roommate brother's friend. He hired me for his firm. It doesn't seem that far-fetched. In fact, it's not far-fetched because, as Granovetter shows, that's how most people get jobs. Why does that happen? Well, let's look. Remember, we've got 151 neighbors, 2,900 2 neighbors, and 229,000 3 neighbors. There's so many more of these 3 neighbors that they're just that much more likely to get you a job. They're also that much more likely to introduce you to the person you're going to marry. They're also that much more likely to tell you about a great new place to live or a place to go on vacation. It's just the sheer numbers. So this puzzle, the sort of strength of weak ties puzzle, this idea that sort of loose connections get you things, isn't a puzzle once we write down a model and do a little bit of math. Let's look at other network structures. So here's a network of collaborations among scientists. What you see that there's sort of some people who collaborate more with others. They're more central to the production of knowledge. And if we think back to our internet model, our World Wide Web model, we saw that we got that power law distribution. So there was some nodes that were connected to a lot, and most nodes were connected to few. What are the functionalities of this sort of network? Well, here's an interesting functionality. Suppose I think about random node failure. So suppose nodes on the internet are going to fail randomly. Well, most nodes are connected to very few. Most nodes are over here. So that means if you have random failure, this node is going to be incredibly robust. So no one said, hey, let's make connections in such a way to make the internet robust. But in fact, that emerges from the structure of the network. What about targeted failures, though? Suppose people wanted to shut down the internet. Well, if you wanted to target failure, then you'd go after these, the ones with lots of connections. So it turns out the internet is really robust to random failure, but it's not at all robust to targeted failure. Those are functionalities that emerge from the preferential attachment rule. Nobody built them in, they just happen. So what have we learned? We learned it's sort of fun to talk about networks, there's pictures, but we can really unpack it in a formal way by constructing models of networks. Those models of networks can focus on the logic. How does the network form? The structure. What are the statistical properties of the networks? And then finally, the functionality. What does the network do? Right? Is the network robust to random failure? Is it robust to strategic failure? Does it give us 6 degrees of separation or 400 degrees of separation? Is it connected or not connected? So there's all these functionalities that emerge from the network structure, and the network structure in turn is a result of the individual logic for how people make connections, or how firms make connections, or how web pages make connections. One last thing before I conclude this set of lectures on networks. Now that we have networks and we understand the functionality of those networks, we can think about interventions into the network. So here's, again, a social network, but suppose we wanted to ask that there's some disease that's going to spread. Now remember we talked about our model of vaccinations, and we said that you have to vaccinate as a function of the R0. So the higher R0 is, the more people you have to vaccinate. But that was assuming that people were randomly connected and that everybody was sort of randomly meeting other people. But in real social networks, you'll see there's some people like this person here and these people here that are much more central to the node, much more central to the graph. They're connected to lots of people. These might be school teachers. These might be bus drivers. So if you think about vaccination, rather than saying, okay, blanket, we've got to vaccinate 20% of people or 30% of people based on R0, instead you can look at the social network and say, oh, you know what, we need to vaccinate these people, these people, these people, these people. So by profession, you might be able to figure out by profession, who are the most important people to vaccinate to prevent this thing from spreading. So by combining our network model with our disease model, our SRR model, we can actually come up with lower vaccination rates to stop the spread of diseases. So again, this is why you want to be a many model thinker. Because if you've got lots of models in your head, you can then combine those models in interesting ways. So we have the vaccination model, which says the more virulent the disease, the more people we have to vaccinate. Now we've got this network model that says, well, no, everybody's not connected, everybody with equal probability. The random graph model isn't true of social networks. So then you realize what really matters isn't vaccinating everybody, but vaccinating the key people to prevent the disease from spreading. And what you'd like to do is make the network, by snipping off people, disconnected. Because if it's disconnected, then it can't spread. Okay, so we've learned a lot about networks, their logic, their structure, and their function. And we've seen how we can apply them in the disease model. But if we take a lot of the models we've done in class, you can also throw networks in. So a lot of research that's been done in the last 10, 15 years in the social sciences has been to add networks onto things like economic performance, school performance, things like that, to show how these sort of interactions between individuals have an effect on what's happening at the macro level. All right, thanks.